Okay, so continuing on, this should be somewhat familiar to you. The wave properties of the electrons, all of that background information up to Niels Bohr, learning about the movement of electrons and energy being released and things like that, led to a better understanding of how electrons are arranged within atoms. So we couldn't see the electrons in 1900. So therefore, we didn't have a way of visually seeing them, but scientists were figuring out that these things existed and that there was energy within them, and then the arrangements were special. So every element had a unique arrangement. So after World War I, Niels Bohr continued to work on this knowledge or this study of the behavior of electrons in the atoms. And so he was, of course, looking at it as if it was a particle, so it had mass, because we know the electrons have mass. And Erwin Schrödinger came along, and he was trying to do the same thing, but he was looking at it from a wave perspective. And so his approach actually became even better, because he actually started looking at the atom as a three-dimensional space and realizing that there's a three-dimensional area or volume in which these electrons could be located. And so Schrödinger is very is warranted with having this idea of quantum mechanics. And so we're not going to go deep into quantum mechanics. It's very heavy physics. And so the quantum mechanical model, we're going to go into the overview of it, and we're not even going to get into the quantum numbers. You can learn those in your high school or your college chemistry class or in a quantum physics class or whatever. But we're not even going to get into that. We're going to simplify it and make it kind of an easier method for us to recognize. But basically what we come down to is Werner Heisenberg and Max Born provided this uncertainty principle. So the uncertainty principle basically is that with electrons in one approach, the electrons are moving. So in Schrödinger's approach, we said the electrons are moving. But if the electrons are moving, how do we know where they are? And so if we choose to know one, which is the energy of the electron, right, then we have to realize that we don't know anything about where it is in space. We can only look at one or the other, because if it has energy, it's going to be moving with a velocity. Well, that means that it's never in one specific position. So you can't pinpoint, because it's always constantly moving. So that's where like Erwin Schrödinger really helped us take his probability model of the quantum mechanical model and apply it to this three-dimensional space of the atom and where the electrons are located. So to kind of understand, Erwin Schrödinger came up with this overall shapes of atomic orbitals which help subdivide, for lack of a better way to say it. We call them sublevels, but it helps subdivide the volume of the atom itself. So we have different atomic orbitals. We have the s orbital, which is like a spherical ball-shaped region. And then we have the p orbitals. The p orbitals, there's actually 3 p orbitals. So they basically overlap. So you're not going to see that drawn in this picture, but really, oops, that's not my pen. So really what you're going to see here with these is that these 3 would actually be overlapped to make 3 different smaller regions, but it's one p orbital or p region. And then we have Ds, which are these like clover looking ones, and there are 5 of those. So notice there are 3 p orbitals. And we have 5 d orbitals. So these numbers should look somewhat familiar to you. And then you can see the f orbital gets even more complicated when we look at the f's, and we see that we've got 7 f orbitals, right? So we can see that this gets a little bit complicated, right? And these are regions where electrons would be located. So we would have a single electron in each of those locations. So in the like s orbitals, we would have 2 electrons in there. In the p orbitals, each of these individual things would have, and I know you can't really see that because it's green on that light blue, but each of those p orbitals holds 2, which is a total of 6 electrons itself. So let's move on and talk about how this applies to our electron configurations. So Schrödinger came up with the quantum mechanical model, which is that there is a reasonable probability if we break down the electron cloud into individual small subsects, right, that we can basically pinpoint where there's a high probability of an electron to be existing at any given point. But it will be constantly like a game of musical chairs where they're constantly moving in and out of those locations. So the electron configurations are like a map of where the electrons could be at any given time. So we tend to map our electrons in the ground state as if they're in the lowest energy level, and we pretend like they're not moving, which we know they really are. So when we draw an electron configuration, we're going to be drawing electron configurations for ground state atoms. So the chemical properties of our atoms and our elements depend on those number and arrangement of the electrons. And so when we look at valence electrons, which are the outermost energy level electrons, those are the ones that play a role in our overall bonding and the behavior of how they chemically act with other atoms. So electrons play a huge role, so being able to understand how they're arranged plays an important part. So there's 3 rules. One is the off-ball principle, which basically says that electrons in the ground state are always going to fill the lowest orbitals out. So we're going to assume that we're always occupying the ground state, or the lowest or closest to the nucleus as we can. We're not going to talk about excited state electrons because that becomes more complicated. The Pauli exclusion principle says that you cannot have 2 electrons in an atom with the same set of quantum numbers, which basically means that 2 electrons must have what we call opposite spins to be able to occupy the same orbital. That really has to do with the fact that when we look, if you look right down here, it kind of explains it with the electron spin. We have one electron that is north, that is creating a magnetic field, that is north facing upward, whereas one where it is north facing downward. So really what they do is they have opposite magnetic fields. And that, when they have opposite magnetic fields, allows them to occupy or be attracted to each other. Because normally, a negative electron would not like to be next to another negative electron. But if they're rotating in opposite directions and creating opposite magnetic fields, those 2 electrons actually will create an attraction to each other. But if I tried to introduce a 3rd electron there, that's going to jack it all up. So that's Pauli exclusion principle. So when we draw the 2 electrons, we always draw one up and one down to indicate those opposite spins. Hund's rule says the most stable arrangement of electrons is that with the maximum number of unpaired. So they prefer to have their own orbital before they pair, because again, 2 negatives aren't going to love being next to each other, but if they have opposite spins, it can work. But if they have the choice, they would rather be as far away from each other as possible. And so that's where that, again, electron spin becomes important. So with the electron spin, that's where we get magnetism. So it's kind of neat. You don't have to go into depth on this, but basically magnetite is an iron oxide compound that is actually magnetic. So William Gilbert actually in 1600 concluded the Earth is also a really large spherical magnet because the Earth's core is made of magnetite. And so with a magnetic south at the geographic North Pole. So when we think of geographic North Pole, that's really the south side of the magnetic end of our large Earth magnet. So never forget, opposites attract and likes repel. So even if it's opposite poles of the magnet or opposite electrical charges, we'll use that a lot this year. So you can have different, depending on how the electrons arrange themselves within the electron cloud, that in that valence energy level, that determines whether or not something is magnetic or not. So diamagnetic means the magnet dies. It's not magnetic. So some things are not. So they are slightly repelled by the magnetic field. This occurs when all the electrons are paired. So if all electrons in our metal are paired, then we end up as being a magnet that doesn't isn't magnetic, right? So no magnet. Paramagnetic is things like iron and whatever that are attracted to a magnetic field. They lose their magnetism when removed from a magnetic field, though. So that's why you can have a piece of iron, magnetic iron or whatever, and it over by itself, it doesn't have the magnetic field. But when I bring two magnets near each other, I see that they get that magnetic property because of the magnetic field. So paramagnetic has one or more unpaired electrons. Ferromagnetic is actually the same concept, but it's basically magnetism, something that retains magnetism upon introduction and then removal to a magnetic field. So sometimes something like iron or whatever, something might not be magnetic, but if we expose it to a magnetic field, it creates a shift in the electron pairings and it creates it and makes it stay as magnetic. So it's kind of a neat thing. So this kind of goes into the background of why, and it is kind of neat, but it's not really, again, something you need to 100% know. Sometimes they like to throw in the diamagnetic and paramagnetic definitions on the AP exam and the multiple choice or something. But it's very unlikely you're not going to see, you're very unlikely you're going to see it. It's usually a little bit smaller, less important. All right, so we're just going to move on and jump into writing electron configurations. So up at the top, I just kind of did an overview of your different energy levels. I really love this orbital diagram right here because it helps you kind of see how the energy increases. So I typically use the periodic table method, though, where I start from energy level 1 and I move across the periodic table and going row by row because I feel like it helps you put it in order of increasing energy. So you're going to write the orbital diagrams for the following. An orbital diagram is when you draw it with the arrow. So I'm going to do this example for you. So with sodium, if I was going to draw the orbital diagram for sodium, I would find where it is on my periodic table, which is, it's right here, if you did not know. It has 11 electrons total, so you want to make sure you know that so you can get the right number. So I would start with 1s, and we just do it in a singular line. We draw one space for that 1s orbital, and there's 2 electrons, so an arrow up and down. And then we go to the next energy level, which is 2s, and that's going to have 2 electrons. Continuing in that energy level, we would have 2p, but as I said before, p has 3 orbitals. So it's going to be 1, 2, 3, and then this 4, 5, and 6 are down. And then we go to the third energy level, which is where that last electron is. There's only one more electron left to give me 11, and so that would be my 3s. If I wanted to do the Lewis dot structure for this element, the Lewis dot structure shows the valence electrons. So remember, valence electrons are the outermost electrons. So when I look at this, I would look at this 3s1 right here. And so, oops, I didn't mean to do that in a highlighter, but that's fine. So I would look at this. And then from there, I would put sodium in the middle, Na. And I would put just 1 dot. I always start at the top, but it doesn't really matter. But I usually start at the top and rotate around. So I am not going to do them, but you will, and they will be in your notes that you submit to me. I want you to do the same thing for arsenic and for iron. Make sure when you get to iron and arsenic that you realize that the direction. So you're going to go 4s and then 3d and then 4p to get to the arsenic. So pay close attention to that. When you follow along on your periodic table, the order of the electrons and the orbital diagrams would go in that same orbit. All right, so do those, and then you will submit those, and we'll check those in class. The ion electron configurations are similar, but they are a little bit more. You have to remember that ions are going to gain or lose electrons. So for cations, remember there is a loss of electrons, and so your valence electrons are going to be the first ones to go. The shell energy ranges separate more widely, and we'll talk about this more later. So atoms and ions with unpaired electrons are considered, remember, paramagnetic. So they would be attracted to a magnetic field. It doesn't mean that they are going to be magnets, but in the magnetic field, they may have a magnetic property. Transition metals with a +2 or higher are going to have no s sublevel electrons, and so we'll talk about why. And Fe +2, which is the one we're going to do, is paramagnetic to the extent of 4 unpaired electrons. So I'm going to do both of these. So we're going to do Fe +2 first. So when I go to do the iron, which you should have done neutral iron up at the top, when we look at that neutral iron, I'm going to do it with an electron configuration. I'm going to go ahead and do the orbital diagram. So it would be 1s, 2s, 2p, with 3, and so we've got 3 up, 3 down, 3s, 3p, oops, it's 3. All right, and 4s is what we're going to do, and then you're going to have 3d, which has 5, 1, 2, 3, 4, 5. So when you look at your d's, for your iron, you're going to end up having 1, 2, 3, 4, 5, 6. So you're going to end up having 5, and then the last one's going to be paired. So one thing to realize is we lose, whenever we become an ion, we lose valence electrons first. So one thing you want to notice is, what is my valence electron here? Technically, the valence electrons are these 4 s's. So the Fe +2 is going to lose 2 electrons. So technically, it will lose those, if that makes sense. So the D's are still there because they're part of the lower energy level. So the electron configuration for this is really 1s2, 2s2, 2p6, 3s2, 3p6, but then now there is no 4s, it's just 3d6. The F +3, which is the other one, right, would be losing the third, so it would also lose this one. So notice that Fe +2 has that unpaired electrons, which is why it has 4 unpaired electrons, which is why it makes it magnetic, whereas the Fe +3 is also magnetic, but it has 5 unpaired electrons. So Fe +3 would be 1s2, 2s2, 2p6, 3s2, 3p6, and then it would be 3d5 because it lost that other electron. So the orbital diagrams are nice to help you kind of see what's happening in those ions. If it was a negative ion, then we would be adding to fill whatever that is. Okay, so for the end of this, I am not going to do all these electron configurations for you. I want you to do these ones up here by yourself. So do those, and you also will submit these in exercise 8. Will be part of the pages that you submit for your homework. And then exercise 9, I'm just going to remind you how to do one of the noble gas configurations because those are the shortcuts. So on these ones up here, you can't do the shortcut, but on this one, exercise 9, you can. So germanium is Ge element. So if I want to do the electron configuration in noble gas shortcut, we're going to go to the noble gas that comes before it. So the noble gas that comes before germanium is Ar. So I put Ar in brackets. You can only do this with noble gases. And then we write for the very last row. So I would write 4s2, 3d10, and then it would be 4p2. So that would be my electron configuration with the noble gas shortcut. So basically, you're only showing the last energy level, including the 3Ds, though, because they technically fall after the 4s. So then this would tell me that I have 4 valence electrons, right? So if I was going to do the Lewis structure, it would be Ge with 1, 2, 3, 4 unpaired electrons. So that way you could see that. Technically, when you look at your 4s2, you would have 2 paired and 2 unpaired, but it's fine. So what I want you to do on these is I want you to do the rest of them. So silver, and then don't forget, so those are silver atoms, and then strontium +2 and cesium +1, those are the ions. So make sure that you have shown the loss of those electrons to show what it would look like. And remember, we always lose from the S's before we lose from the D's. So you would always lose from your outermost energy level first. All right, and this very last part is called an isoelectronic series. Basically, an isoelectronic series are atoms or ions that have the same electron structure and the same number of valence electrons. So iso just means they have the same, and electron means number of electrons. So we can figure this out really quickly and really easily with the exercise number 10. I'm just going to do that one, and you guys can do 11. But basically, it says circle all of them that are part of the isoelectronic series for neon. So neon atom, when we look at that, has 10 electrons. So we're looking for all of them that would have 10 electrons. So for example, selenium. Selenium has 34 plus 2, so it has 36 electrons. So selenium would not be isoelectronic. Sulfur has 16 plus 2, so it has 18, so that's not isoelectronic. Fluorine has 9 plus 1, so it's got 10 electrons. So fluorine is considered isoelectronic because they have the same number of electrons. Oxygen is 8 plus 2, so therefore that's 10, so oxygen ion is going to be isoelectronic. Phosphorus has 15 plus 3 is 18 electrons, so that would not be isoelectronic. Aluminum has 13 minus 3, which gives it 10, so aluminum ion is isoelectronic with the neutral neon. And then sodium is 11 minus 1, so that's going to be 10 electrons, so sodium would be isoelectronic. So as long as they have the same number of electrons, they're going to have the same electron configuration in the ion state, okay? Their neutral atoms will not have the same electron configurations. All right, so I want you to also answer this last question before you submit your video notes. All right, and please come to class with any questions. We'll work on this, but I know it's mostly review, so it should go pretty quick in terms of you being able to put me on speed, listen, or whatever. And we will talk about this a little bit more next class.